Okay, ready for part 3 of this vision of linear algebra. So the key word in part 3 is orthogonal, which again means perpendicular. So we have perpendicular vectors. We can imagine those. We have something called orthogonal matrices. That's when, I've got one here. An orthogonal matrix is when we have these columns. I'm always going to use the letter Q for an orthogonal matrix. And I look at its columns, and every column is perpendicular to every other column. So I don't just have two perpendicular vectors going like this. I have n of them because I'm in n dimensions. And you just imagine x, y, z axes, or x, y, z, w axes, go up to 4D for relativity, go up to 8D for string theory, 8 dimensions. We just have vectors, after all. It's just this row of numbers or a column of numbers, and we can decide when things are perpendicular by that test, like, say, the test for Q1 to be perpendicular to Qn is that row times that column. When I say times, I mean dot product, multiply every pair. Q1 transpose Qn gives that 0 up there. So the columns are perpendicular. And those matrices are the best to compute with. And again, they're called Q. And one way to do a quick matrix way, because there's always a matrix way to explain something, and you'll see how quick it is here. This business of having columns that are perpendicular to each other, and actually I'm going to make those lengths of all those column vectors all 1, just to sort of normalize it, then all that's expressed by, if I multiply Q transpose by Q, I'm taking all those dot products and I'm getting 1s when it's Q against itself, and I'm getting 0s when it's one Q versus another Q. And again, just think of 3 perpendicular axes. Those directions are the Q1, Q2, Q3. Okay, so we really want to compute with those. Here's an example. Well, that has just 2 perpendicular axes. I didn't have space for the third one. So do you see that those 2 columns are perpendicular? Again, what does that mean? I take the dot product. -1 times 2, 2. 2 times -1, another -2. So I'm up to -4 at this point. And then 2 times 2 gives a +4, so it all washes out to 0. And why is that 1/3 there? Why is that? That's so that these vectors will have length 1. They'll be unit vectors. Yeah. And how do I figure the length of a vector? Just while we're at it. I take 1 squared, or -1 squared gives me 1, 2 squared, and 2 squared. I take the dot product with itself. So -1 squared, 2 squared, and 2 squared, that adds up to 9. The square root of 9 is the length. I'm just doing Pythagoras here. There's one side of a triangle. Here's a second side of a triangle. It's a right triangle because that vector is perpendicular to that one. It's in 3D because they have 3 components, and I didn't write a third direction. And they're length 1 vectors because just that's how when I compute the length and remember about the 1/3, which is put in there to give length 1. So, okay. So these matrices are with Q transpose times Q equal I. That again, that's the matrix shorthand for all I've just said. And those matrices are the best because they don't change the length of anything. You don't have blow up. You don't have going to 0. You can multiply together 1,000 matrices and you'll still have another orthogonal matrix. Yes, a little family of beautiful matrices. Okay, and very, very useful. Okay, and there's a good example. Oh, I think the way I got that example, I just added the third row. The third column, sorry, the third column. So 2 squared plus 2 squared plus -1 squared, that adds up to 9 when I take the square root, I get 3, so that has length 3. I divided by 3, so it would have length 1. We always want to see 1s like we do there. And here's a simple fact, but great, that if I have 2 of these matrices or 50 of these matrices, I could multiply them together and I would still have length 1. I'd still have orthogonal matrices. 1 times 1 times 1 forever is 1. Okay, so there's probably something hiding here. Oh yeah, to understand why these matrices are important, this line is telling me that if I have a vector x and I multiply by q, it doesn't change the length. This is a symbol for length squared, and that's equal to the original length squared. Length is preserved by these q's. Everything is preserved. You're multiplying effectively by the matrix versions of 1 and minus 1. So, and a rotation is a very significant, very valuable orthogonal matrix, which just has cosines and sines, and everybody's remembering that cosine squared plus sine squared is 1 from trig, and that's an orthogonal matrix. Oh, it's also orthogonal because the dot product between that one and that one, you're okay for the dot product? That product gives me minus sine cosine plus sine cosine 0. So the column 1 is orthogonal to column 2. That's good. Okay. These lambdas that you see here are something called eigenvalues. That's not allowed until the next lecture. Okay. All right. Now here's something. Here's a computing thing. If we have a bunch of columns, not orthogonal, not length 1, then we would like to convert them to, so call those A1 to AN. Nothing special about those columns. We would like to convert them to orthogonal columns because they're the beautiful ones, Q1 up to Qn. And 2 guys called Graham and Schmidt figured out a way to do that, and a century later, we're still using their idea. Well, I don't know whose idea it was, actually. I think Graham had the idea, and I'm not really sure what Schmidt, how he got into it. Well, he may have repeated the idea. So, okay, so it just, I won't go all the details, but here's what the point is. The point is, if I have a bunch of columns that are independent, they go in different directions, but they're not 90-degree directions, then I can convert it to a 90-degree one, to perpendicular axes, with a matrix R happens to be triangular, that did the moving around, takes the combinations. So A equal QR is one of the fundamental steps of linear algebra and computational linear algebra. Very, very often we're given a matrix A, we want a nice matrix Q, so we do this Graham-Schmidt step to make the columns orthogonal. And here's the first step of Graham-Schmidt, but you need practice to see all the steps. Maybe not. Okay, so here's what's the advantage of perpendicular vectors? Suppose I have a triangle, and one side is perpendicular to the second side. How does that help? Well, that's a right triangle then. Side A perpendicular to side B. And of course, Pythagoras, now we're really going back, Pythagoras said that A squared plus B squared is C squared. So we have beautiful formulas when things are perpendicular. If the angles are not 90 degrees, when the cosine of 90 degrees is 1, or maybe the sine of 90 degrees is 1, yeah, sine of 90 degrees is 1. For those perfect angles, 0 and 90 degrees, we can do everything. And here's a place that Q fits. Just to make this is like the first big application of linear algebra. So let me just say what it is, and it uses these Q's. So what's the application? It's called least squares. And you start with equations, ax equal b. You always think of that as a matrix times the unknown vector being a known right-hand side b, ax equal b. So suppose we have too many equations. That often happens. If you take too many measurements, you want to get something, you want to get an exact x, so you do more and more measurements b. You're pasting more and more conditions on x, and you're not going to find an exact x because you've got too many equations. M is bigger than n. We might have 2,000 measurements, say from medical things or from satellites, and we might have only 2 unknowns, fitting a straight line with only 2 variables. So how am I going to solve 2,000 equations with 2 unknowns? Well, I'm not. But I'll look for the best solution. How close can I come? And that's what least squares is about. You get b, ax as close as possible to b. And probably this will show here's the right equation. Here's my message. When you can't solve ax equal b, multiply both sides by A transpose, then you can solve this equation. That's the right equation. So I put a little hat on that x to show that it doesn't solve the original equation, ax equal b, but it comes the closest. It's the closest solution I could find, and it's discovered by multiplying both sides by this A transpose matrix. So A transpose A is a terrifically important matrix. It's a square matrix. See, A didn't have to be square. I could have lots of measurements there, many, many equations, long, thin matrix for A. But A transpose A always comes out square and also symmetric. And it's just a great matrix for theory. And this QR business makes it work in practice. Let me see if there's more. So this is, this is the geometry. So I start with a matrix A. It's only got a few columns, maybe even only 2 columns. So its column space is just a plane, not the whole space. But my right-hand side B is somewhere else in whole space. You see this situation? I can only solve AX equal B when B is in this, when B is a combination of the columns. And here it's not. The measurements weren't perfect. I'm off somewhere. So I have, how do you deal with that? Geometry tells you, you can't deal with B. It's not going, you can't solve AX equal B. So you drop a perpendicular. You find the closest point, the projection, that in the space where you can solve. So then you solve AX equal P. That's what least squares is all about. Fitting the best straight line, the best parabola, whatever, is all linear algebra of perpendicular things and orthogonal matrices. Okay, I think that's what I can say about orthogonal. Well, it'll come in again. Orthogonal matrices, perpendicular columns is so beautiful. But next is coming eigenvectors, and that's another chapter, so I'll stop here. Good, thanks.